to this installment of the FDTD Goes Our Satellite Applications webinar. We're happy today to have Chris Bedka, who works at the NASA Langley Research Center. Chris has spent about 15 years examining storm-top structures with satellite imagery. He's going to be talking today about the above Anvil Cirrus plume, AACP for short. Go to the next slide, please. So this is part of the FDTD Go 16 webinars, or satellite chat, as has been called in the past. We're always looking for speakers, so email me, Scott Lindstrom, or Dan Bykos at dan.bykos@noaa.gov, scottlindstrom.noaa.gov, if you have a topic where you're using GOES 16 or GOES 17 data to help you in decision services and an operational desk. Next slide, please. Just some protocol. There'll be about 20 minutes. We'll be done actually by 18:30Z, not 17:30. Chris will talk about 20 minutes, and they'll have questions. You can send them to the chat, or we'll ask at the end of the talk. Please mute your phone when you're not speaking. Don't press hold. Take it away, Chris. Thanks.
All right, thank you very much, Scott. So I'll start off with a introduction to above Anvil Cirrus plumes, or you'll see either I refer to them interchangeably as plumes or AACPs. So we found in a recent study collaborating with Cameron Homeyer from the University of Oklahoma, who is one of my co-authors on this research, we found that AACPs indicate the presence of really an especially intense updraft occurring in an environment where you have strong storm-relative wind shear, so that takes into account the storm motion and the ambient flow to derive the wind shear. And so when you have this, we have overshooting tops all the time, but you don't necessarily see plumes being generated from them. So these are a special subspecies of storms where you have this really incredibly strong updraft coupled with the shear, and that helps to generate unstable layers near the cloud top, which enables gravity wave braking. And then that gravity wave braking enables detachment of cirrus cloud material from the overshooting area, and then the ambient winds projected downstream. And you can have these plumes, as you're seeing in the lower left, in some storms over North Dakota, and then the lower right in storms over Nebraska and South Dakota here. You see that these plumes can stretch for sometimes hundreds of kilometers and be generated for several hours continuously. And so we're seeing in this imagery here, in the visible image, so this is the sandwich product, where you're taking the infrared data and kind of superimposing it upon the visible, so you get that three-dimensional texture from the visible coupled with the temperature information from the IR. And you can see that the vertical separation of the plume cloud relative to the underlying anvil, and also what appears to be somewhat unique cloud microphysics in the anvil, cause these plumes to exhibit a unique texture in the visible imagery. Also, previous research from Martin Sesvac and colleagues in Europe have found that you can look at the 1.6 micron or 3.9 micron, the reflected component of it, to identify plumes. But in recent research that I've done, it's not always necessarily the case, but I encourage further research from the operational community and looking into that, because there may be some signal there as well. So you get this temperature contrast between the plume and the underlying anvil due to the upper troposphere, lower stratosphere temperature structure. If you have a very sharp inversion at the stratosphere and plume material be emitted several kilometers into the stratosphere, your plumes will appear quite warm relative to what you expect the underlying anvil to look like, which is typically around the equilibrium level temperature where the anvil resides. And so you see this anomalous warm pattern here. So you're seeing this yellow embedded within the anvil that's typically blue, and that's about at least a 10-degree temperature contrast, if not more, between the plume and the anvil. Where you have situations where you have maybe isothermal tropopause or a double tropopause structure, sometimes you can get cold plumes where you see a really obvious signature in the visible, but it's not necessarily appearing anomalously warm in the infrared. Those are more uncommon than the warm plumes. Some of you may have heard of the signature called the enhanced V. And so you're actually seeing that pattern in the lower left, where you see this blue-shaped area of very cold temperatures, and then this warm material in between the kind of two arms of the V or U shape that you see there. That's the plume. So the above Anvil Cirrus plume and enhanced V are tightly related. And I'm not going to claim to have discovered the enhanced V. This has been researched for probably over 30 years by many folks, starting in the early 80s. But what we're trying to do here is understand what does this plume mean for you as operational forecasters, and just raise some awareness about the seriousness of storms with that plume signature. And then hopefully the operational community will find some use for identifying it and continue to expand upon this research. Just to kind of give you an idea, we're looking right now at one of the more recent severe storm outbreaks on 5 May 2019 across Texas and the plains. On the left, I have GOES infrared imagery, and I apologize for changing the color enhancement on you, where here the dark maroon and red colors are cold, where the yellows and lighter oranges are warmer. And so where you're having yellow embedded within the red or maroon, that's again about a 10-degree temperature contrast there. And you see that I've numbered the storms 1 through 9, and I did a screenshot of my radar scope just sitting at home one night as these storms were popping up, and you can see that all of these plume signature storms have some sort of warning associated with them, whether it be a severe thunderstorm or a tornado. So it's clear that you're recognizing signatures in the radar, in the lightning data that's causing you to issue warnings. For the top of the storm, there's some really interesting behaviors going on as well, as depicted by GOES 16. Just another couple random snapshots here where I identified plume storms with arrows, and you see these kind of anomalous patches of warmer temperatures embedded within the colder Anvil surrounding, which should be a clue that, hey, something weird's going on with this storm, and it's actually because the updraft is so strong, it's penetrating into the stratosphere and then releasing cirrus that's emanating at the ambient stratospheric temperature. And so, historically, I know what to look for, so I found these signatures in GOES 8 to 15 data. But imagery every 15, sometimes as latent as or as infrequent as every 30 minutes at full disk scan times in the past. You might see the signature late, or sometimes if the imagery is a little blurry or blocky, you weren't really able to see it at all unless you really knew what you were looking for. And so nowadays, with GOES 14 in experimental mode a few years ago, looking at 1-minute data, and then GOES 16 where we're getting routine 1-minute data, this really allows us to more precisely determine when and where these plumes were produced. So what we decided to do is look at a large sample of manual plume identifications based upon 1-minute or better imagery from GOES 14 and 16, doing some objective storm tracking from radar data, gridded radar data, pairing the storm tracks and the plume identifications with NWS warnings and severe weather reports, and looking at many different storm outbreaks to answer science questions such as, what is the severe weather frequency for plume storms compared to those without plumes? Are certain severe weather types more likely to be produced by these storms? How far in advance do they occur ahead of severe weather reports? Do these plume storms have any relationship with supercells? And then how can severe weather warning perhaps be helped by knowledge that the storm is producing a above Anvil Cirrus plume? So just kind of a schematic here, kind of giving you an idea of what we're doing. So you see, obviously, convective storms are quite complex. They rotate. You can see how fast the outflow is being emanated from overshooting tops using cloud top tracking. A lot of different information we have here. So we're trying to put it all together. So satellite observations, various metrics of storm intensity from NextRad, total lightning flash rates from a ground-based network. Our studies were during 2017 when GLM wasn't quite ready for prime time. But obviously now GLM is looking great. But here we are using a ground-based total lightning network, Earth networks, severe weather reports, and severe weather warnings to really unravel what do these plume signatures mean for weather forecasting. And so here, the radar NWS is quite familiar with it, but here we're using a relatively new product derived by Oklahoma and the Texas A&M teams called GridRad. So basically, it's based upon the premise that if you have a storm in a certain location, chances are it's viewed by many different radars. And so with your 14 or so elevation slices from each NexRad radar, you can end up with almost as many as 100 individual slices through a particular storm. And so my colleagues at A&M in Oklahoma have pieced this data together and built pretty high-resolution vertical and spatial resolution composites of these storms. So it's similar to the MRMS system that NOAA has developed over the years, but it really emphasizes the three-dimensional structure of the storm, especially focusing on the upper troposphere and lower stratosphere. My colleagues are very interested in looking at troposphere-stratospheric exchange by overshooting convection, so they really wanted to be sure to get the 3D structure right. But within this product, you have all sorts of different fields, echo tops at varying DBZ levels, radial divergence, azimuthal shear, and all sorts of things that you all are accustomed to looking at from radar perspectives. So you see in the lower left is just kind of an isosurface of the radar, and where we have these really high peaks of echo tops. These are some storms that are producing plumes in the infrared, as I show in the lower left. And there's just a cross-section of what some of this GridRad data looks like, pretty standard for those that are familiar with looking at radar data. And so we take this data, we associate 40 DBZ echo tops every 5 minutes and develop storm tracks. And so there's an example from a outbreak back in 2014 viewed by GOES 14. And so these storm tracks, if you look at it compared to operationally available storm tracking algorithms, they're quite comparable. There are some advantages, but I don't have time to really go into all that. And so what these objects do is allow you, once you know where the storm went every 5 minutes and you saw its full trajectory, you can use those objects as a bucket. And so you dump in what was the infrared temperature at this time, what was the azimuthal shear, when was the warning issued, and when were the reports reported, these types of things. These tracks allow you to monitor all these things at high temporal resolution and really do some quantitative analysis. And so what we did, we looked at 13 severe weather outbreaks over the years, about 7 or so in 2017, and then some in various other years when GOES 14 was in 1-minute mode. We looked at about 8,000 GOES images, manually analyzed, pouring into them, zooming, rocking back and forth, looking for when we see emission of these plumes. We found about 405 plume-producing storm cells by a couple human experts. And then we had over 4,000 non-plume producing cells. And so we noted when we thought that the starting time of plume production and when it ended, you can have 10 plumes being produced or more simultaneously across several states. So these storms get to be quite prolific. Some storms can produce plumes continuously for 4 hours or more. We found in our study that the mean duration of plume production was about 50 minutes, so this is not just a flash in the pan, one-off kind of thing. Once they get going, they can be going for quite a while. We found over 4,000 severe weather reports from 700 storm cells. 800 plus were significant ones, which we consider to be 2-inch hail, 65 knot or greater winds, and EF2 or greater tornado intensity. We looked at the NOAA NCEI database to extract these reports, and also we looked at warning information from the Iowa Environmental Measurement site. So how do we identify plumes? So in the left-hand animation here, you're seeing infrared data, one of these sandwich-type products where we're superimposing the infrared atop the visible, and the circles that are appearing are storms that we are flagging as being active plume producers right now. So we identify the smoke-like visible texture or a plume-shaped panel of warm infrared temperature anomalies coming from overshooting tops. We then link these identifications to the radar-derived storm cells, and our radar-derived storm cells had to have a lifetime or 10 minutes or more to be able to be part of this. So some of these storms on the left panel, you said, oh, I see a plume there. Why isn't there a circle? Well, it's perhaps you were having splits or other sorts of behavior with the storm tracking that wasn't allowing them to be tracked for a sufficient amount of time. And once you start to look at this data, you realize that these plumes become very easy to identify. It's almost like once you start to see them, you can't unsee them. And I have a habit of doing this. I'm sitting on the couch with my wife. I'm like, oh, look, boom, 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 boom. And then they just start popping out to you really, really clearly, and it's pretty remarkable. And yeah, once you have a team of experts that have looked at enough of these, we found that our uncertainty was maybe plus or minus 5 minutes for plume start and end time. So you get to be quite good once you start staring at these things. Here's an example of some storm tracks just from our various days, 4 days during our study period here. The black lines are the plume storm tracks, and the white lines are just ordinary thunderstorms, we'll call them. And then we superimpose the severe weather reports on top of that. And you see that in many cases that the severe weather reports are concentrated along our storm tracks. Our plume storm tracks. We had no idea what the severe weather report distribution was when we were doing our analysis. It was completely blind to us. We simply stared at satellite images and noted down coordinates and storm cell IDs and other sorts of things. So this is quite robust what you see here. And what we found is that the plume storm tracks are about 45 to 60 minutes longer on average than non-plume storms. So that suggests that these storms are very well organized and robust, and as a result, they're ultimately more likely to be severe. And so when we drill into some of the severe weather reports here, we find that if you take the number of severe weather reports per storm for storms that produce plumes and those without, you end up with about 14 times more reports for plume-producing storms than non-plume-producing storms. And we've normalized this by storm lifetime. That's not shown here, but we still find that plume-producing storms are more severe. If you say, hey, this is kind of cheap, you're counting all the null storms in your statistics here. We say, fine, let's look at severe storms that produce plumes versus severe storms that didn't produce plumes. What was the ratio of severe weather for these two storm populations? And we still find that plume-producing storms generate about 2.6 times more severe weather if that's your metric of doing it. Just blindly say, of all your cells, what fraction of them produced severe weather? Is about 59% of the storms, plume-producing storms, which were severe. So it's greater than a coin flip, which is pretty powerful. Even more importantly, if you take the whole population of really significant severe weather reports and you say what fraction of those were attributable to plume-producing storms, we find 73% of them were. So almost 3/4 of the significant severe weather across 13 severe weather outbreaks were produced by these plume-producing storms. We also dug a little deeper here. Well, just a quick note above that, you see that over 85% of the really significant tornado and hail events were from plume-producing storms, whereas wind reports were much lower, and I'll get into that in a second. Also, supercells. So we had some graduate students really pour into the data here, look at where they define supercells using a whole combination of quantitative metrics like a long storm lifetime, a really high echo top, rotation metrics, or you can look at qualitative signatures like looking for hook echoes, B-wares, deviant motion relative to others. About 194 supercells in our population. And 48% of the plume storm population were supercells. Now you flip that around, you say, of those 194 supercells, what fraction of those produced plumes? And it was about 3/4. So it seems that based upon this infrared and visible metric of patterns in the cloud top, you can, with pretty decent ratio, you can see that where some of at least the most intense supercells are present just based upon the imagery alone, which is powerful, especially in regions where you don't have radar data and satellite's the only gig in town. Having the capability to identify supercells based upon infrared and visible patterns in cloud top is really powerful. Talking about damaging winds here, these are just 4 random damaging wind-producing storms going from 61-knot winds all the way up to 96-knot winds. And you see that all 4 of these produce some form of above Anvil cirrus plume, and I identify that with those white arrows in the left panel there. And so you say, well, why do you only end up with 41% of the significant winds produced by plume-producing storms? What we find in these wind producers and MCSs is that the storm object IDs from radar tend to change more frequently. You have a lot of cells maybe along a bow echo or some sort of squall line there, and the cells don't seem to remain discrete quite as long or as well in wind-producing storms than in MCSs than in say supercells and things like this. And so we had this requirement that said that the storm ID had to be 10 minutes or longer, and so I think the low fraction of wind, significant wind and plume relationship, I think that's driven by our analysis approach, and not necessarily maybe a physical process, although there might be some differences in physical process as well, whereas winds are generated by downdrafts, whereas hail and tornadoes are maybe more of an updraft-driven process. So there's
Chris, this is Scott. I want to leave time for questions, so could you skip down to your the picture of the paper that you have out on this and then wrap it up?
Yes, I guess. Although you started 5 minutes late. Just really quickly here, if you look at the relationship between when the first severe weather warning was issued and then when the plume was found, you find that there's a pretty similar distribution here, so that when you first recognize a plume, I think it can be a valuable indicator of when the storm is really getting going. But I have to skip a lot of stuff here. So again, as you look at these various metrics, you continue to see that storms with the plumes and when the plume is being produced, updrafts are stronger, lightning flash rates are more frequent, and storm outflow rates are more intense. And so there's a variety of other box and whisker diagrams that you can look at your leisure here, related to radar-based metrics and satellites and lightning-based metrics as well. Here is the weather and forecasting paper published in October 2018, myself as a lead author with our co-authors right here. And so in summary, you heard a lot of this already, and as I noted, the bottom panel, when you see this data, especially where you don't have radar information, the finding plumes can be very valuable for severe weather recognition. So with that, I'll take questions.
Thanks, and I'm going to ask one. I'll take a host prerogative. I've heard about a warm trench. It's associated with the overshooting top, typically downwind of it. Is a warm trench actually you're seeing the cirrus plume in the stratosphere, or is it something different in the storm structure?
I think it depends upon the nature of how the imagery is behaving. Sometimes you do indeed see almost a ring of warmth around an overshooting top, but you don't necessarily see this warmth emanating away. It seems pretty constricted to just the very immediate area around the overshoot. And so I think that you want to look for a projection or a plume of warm temperatures going downstream rather than just hanging around just the immediate circle around the overshoot.
Okay. Are there any other questions for Chris?
Hey Chris, this is Daniel Neatfeld, and great presentation, interesting work for sure. one of the things I think about a little bit is, areas where there's not very good radar coverage, like in the West, and I wonder if you've looked specifically at sort of the western half of the United States to see if you can, compare some typical statistics of, and I know that the reports are really scarce too, but it would just be interesting, I guess, to take a look at that issue and see if some improvement in warning services could be seen with using this technique.
That's a wonderful question, Dan. Thank you for asking. So I've seen plumes throughout the world. All throughout the world. I've seen them in storms over Arizona and certainly New Mexico. Really hot spot of them are the Sierra Madre over northwest Mexico. Those storms really get cranking in the summer, and I see some just hellacious storms with really obvious plumes. And so, as you note, if you start to compute relationships, you get into report sparseness and other things, and that could give one the impression that maybe the signature isn't very useful. So the study was supported by NASA, and we had a lot of different initiatives that we were looking at. So ultimately, we didn't have a lot of time to dig into the details like you described, but that's an area that's ripe for future work by the operational community.
Yeah, it sure looks like it could be really useful.
Hey, this is Bill Line from the Pueblo, Colorado office. I could comment on operational utility if you'd like.
Please do.
At least what we've experienced. I think it obviously goes without saying that radar is always king in warning us, but as you guys mentioned, we do have poor radar coverage in the CONUS. But even aside from that, we have a lot of radar outages with our aging network of radar across the country. So in situations where, at least experienced in my office, where we do have poor radar coverage, and especially when, even with pretty good radar coverage, if you have an event where maybe what you're seeing in radar is pretty borderline and you're kind of on the edge of warning, I think that seeing this feature and knowing the statistics, especially knowing for a lot of offices their verification rate for severe thunderstorm and tornado warnings, looking at ranges from anywhere 30% to 45%, so that's below your, I think you said 59% of plumes produce severe. So seeing this feature, and if you're on the edge of what you're seeing in radar, I think that could be a good tipper for you, and it has been for me. In Pueblo in particular, we do have a lot of these marginal events, maybe Cape 500 to 1,000 joules, shear around 30 knots, especially on our eastern plains, where it is a poor radar zone for us. In southeast Colorado, beams are shooting roughly 10,000 feet above ground level, so really not indicative in radar of what's going on the surface. So if we do see these plumes, we will issue on the storm if what we're seeing in radar isn't really convincing us on the way. So, for example, we had a case last week, and I'm trying to write up a blog post on this one. I wasn't working, but someone else in the office was working. Radar started to show rotation in a storm, and this was in an environment that was could produce a tornadic storm, but this storm just started to show rotation, and of course our radar failed right at that moment. So it was at a point where maybe the warning forecaster wanted to see one more scan, which would have come 1 to 2 minutes later in radar sales mode, but radar data wasn't coming in, so after about 5 minutes, no radar data. Knowing the environment, that storm using 1 minute visible and satellite imagery, he saw that storm started to produce an above Anvil Cirrus plume at that point, and it also had an exposed updraft, so you could actually see the rotation in the visible imagery, and also seeing the continued cold IR temperatures that tipped him to issue a tornado warning on that storm. So a good example of losing radar and knowing what you have in your environment and seeing what you have in your satellite imagery, how that could really push a forecaster over the edge. And that storm actually did go on to produce a tornado a little later. So I definitely think there's operational utility here. In terms of knowledge across the Weather Service, forecasters just aren't used to using satellite data in warning operations. But I think that knowledge is starting to increase. And I think sharing, especially on social media, I think that kind of starts to help spread that knowledge across the Weather Service. And in forums like these, this is really helpful.
Awesome. Thank you, Bill. We have time for one more question? Or two more questions? Whatever.
Speak now or miss this great opportunity.
Yeah, hey Chris, this is Brian Mata. Other than the sandwich product, do you have any other suggestions for which imagery to look at?
There's been some products that I've seen. A colleague of mine, Martin Setbeck, has written about some of the RGB type of composites where you're looking at cloud top microphysics, might give you some additional insights. Although ultimately, really all you truly need is infrared and visible, in my opinion, or just infrared alone in some situations. So I invite the operational folks web service folks to continue to look at various RGBs, and maybe there's something we've missed and that could be valuable. But I'm kind of old school, I guess, and have just stuck with the kind of the baseline data.
What about at nighttime?
Then you're dealing with infrared alone, and so in situations where you have cold plumes, you might start to still see an indicator of the shape of it. Like you're like, there's this weird kind of protrusion of very cold temperatures streaming out from the overshooting top, and that can start to give you an idea, there's some discontinuities here and things look a little weird, and maybe I see a little bit of rotation in my cloud top as well, and so you put all that information together, and that can start to give you an idea of which storms are the nastiest.
All right, great, thanks.
Any other questions? Hearing nothing, I want to thank Chris for this talk. We will have another webinar in 1 week. Kevin Hike from the Duluth office will be talking about finding smoke at night using RGBs. And that's it for today. Thank you again, Chris.